than I expected. So let me carry on. So the operator I haven't talked about yet is this one. And so this one counts the number of times phi winds around the circle. As x runs from 0 to L. So in other words, now once again think about this map. So here's 0, here's L. Yeah, and I have this map to my circle of circumference 2 pi r. And what phi can do a priori, so it can wind around many, many times. Yeah? And somehow what this guy does is it counts how often you wind around if in x space you go around once. Okay? And as a result of this, spectrum of this is also quantized. So its eigenvalues are 2 pi r times n. Yeah? And so that essentially just expresses what I just said. Okay? Because x from 0 to L, this would be a multiple of 2 pi r. So it indeed counts the winding. And also there has to be, it doesn't occur in the mode expansion, but there has to be a conjugate variable to Q, to the conjugate momentum, and I call that Q tilde. Doesn't appear in the mode expansion, but we'll need it later anyway. Okay, so that's the mode expansion of the field, and it's very useful to write this field in terms of right and left moving components. Yeah. And these are defined as follows. Q plus P over 2L dt minus x plus sum n from 1 to infinity, 1 over square root 4 pi n, beta n, e to the I, kn x minus vt, plus beta n dagger e to the I minus ikn x minus vt, and phi left of vt plus x is defined as q bar plus p bar over 2l vt plus x plus some n positive 1 over root n beta minus n, these are the other modes now, e to the minus ikn x plus vt plus beta minus n dagger ikn x plus vt. So these are just the chiral components of the field, and these q's and p's are just sums and differences of the zero mode operators. So q is q minus q tilde over 2, q bar is q plus q tilde over 2, and capital P would be pi naught plus pi naught tilde, and P bar would be pi naught minus pi naught tilde. Okay, so those are the mode expansions as they're usually written in the literature. Okay, and these are still canonical conjugates, so you have Q with P commutators I and Q bar commutator is I. So these are still canonical conjugate variables. Okay, so having in hand these chiral components, we can define the so-called dual field, which will be important later. And this is defined as phi right minus phi left. Okay, as compared to the force field itself was phi right plus phi left. Okay, so that just defines this object. And this is called the dual field. Okay, now, the next thing I want to do is, using this mode expansion I have written there, to work out what the spectrum is of this Hamiltonian. Because, the theory as I've defined it, it's defined in the finite volume. Yeah, so the spectrum will be discrete, and we can calculate actually what it is. So let's do that. Okay, so substitute the mode expansions into the Hamiltonian. Okay, what you get is that this is a normal order Hamiltonian, so I'm throwing away some constants, would be b divided by 4l. Here I have p squared plus p bar squared plus 2 pi b over l. Sum n equals 1 to infinity. Here I have n. And here you have beta delta n plus beta delta minus n, beta minus n. Okay, all I've done here is I've taken the mode expansion, substituted it in the expression of the Hamiltonian, and I've carried out the x integral, which amounts to basically an x integral over these e to the I k x's. Okay? Now the eigenvalues of p and p bar simply follow from the eigenvalues of pi and pi naught tilde, which I derived for you before. So these eigenvalues are just n divided by r plus minus 2 pi r m, where n and m are integers. So that follows from what I did just before we had the break. Alright, but so now you see, you can just read off what is the spectrum of this Hamiltonian, because I've written here what the eigenvalues of p and p bar are. So I can simply work out what are the eigenvalues of p squared plus p bar squared. And here you just have the modes. Yeah, so these are just number operators of the various modes, and they just have integer eigenvalues. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah? And so we can just read off what the spectrum of the Hamiltonian is. So the spectrum of H naught is just E equals 2 pi d over L. Here we have pi r squared m squared plus n squared divided by 4 pi r squared plus sum n equals 1 to infinity n, and here I have mn plus n minus n. Okay? So far so good. So now we make an observation. So this is the same as our free fermion spectrum. The one I wrote for you on Tuesday, okay, if we make some identifications. And the identifications are that B, the velocity in this free boson theory, should be the same as the Fermi velocity in our free fermion theory, which was J A naught sine KF A naught. Okay, and R, this compactification radius, I have to choose as 1 over root pi. Okay, so if I do this, then I claim this spectrum is exactly equal to the free fermion spectrum I wrote for you on Tuesday. So let me just check that I'm lying. Yeah, so that looks pretty good. Okay. So in the free fermion spectrum, so these were these particle hole excitations we had around these Fermi points, and these were related essentially to these excitations where you were backscattering across the Fermi sea, or we're changing the particle number of the fermions. Okay. Good. So now what this shows is that this compact boson theory I have defined, the Hamiltonian of this compact boson theory, has exactly the same spectrum as the Hamiltonian of my free fermion theory. Okay, and so that is already in the finite volume. Yeah, so there are many levels which have exactly the same values for the energies and also the same degeneracies. Okay, so this is already quite a strong indication that these two theories somehow should be equivalent. Yeah? The free fermion theory, so this left dagger dx left minus right dagger dx right, the one I derived to you earlier today, should be the same as this compact boson. Okay? In order to make this identification complete, however, we would like to know how to translate now between operators to the two theories. Yeah? In the free fermion theory, I had this right of x, left of x, and so on and so forth. And here in the free boson theory, I have now to talk about what are the good operators to look at, yeah? And which operators correspond, let's say, to the right Fermi field, to the left Fermi field. Yeah? Because in the fermion theory, essentially I can make almost every operator by just taking products of these Fermi fields. And derivatives, of course. So that's what I would like to do next. So I would like to look at operators in this free boson theory. So before I do that, do you have any questions about this? No? Okay. So what kind of operators can we look at? It's restricted, as I already mentioned in the last lecture, because the boson is compact. Yeah? And it turns out the most important operators are these vertex operators. So operators of the form e to the I alpha, phi right, let's say, x minus vt, or e to the I alpha, phi left, x plus vt. So these are called vertex operators. Okay? And at the moment, I'm saying nothing about what values for alpha I'm allowed to consider here, and so on and so forth. Yeah? So these are the other components of this Bose field, and the Bose field was periodic. Yeah? It was living on a ring. And as I told you in the last lecture, therefore these values of alpha are not arbitrary, so they can only take values in a discrete set. But let me set that aside for now. Let me just look at this object in general and work out some of their properties. And one property I want to work out is, let's say, what are correlation functions of this sort? E to the I alpha, phi right. Let me just say x, e to the I beta, phi right, of x prime. Okay, so let me try to work out what correlation functions of these vertex operators are like. Okay, in order to do this, I will use the mode expansion. Okay. And I will use this Baker-Campbell-Hausdorff lemma. So Baker-Campbell-Hausdorff essentially tells you that if you take the product of exponentials, e to the a, e to the b, and a and b are some operators, this is the same as e to the a plus b, e to the 1/2, commutator a with b, if the commutator is a number. So it's not an operator itself. Yeah? So then these exponentials multiply like so. If the commutator is an operator itself, then it's more complicated. Yeah? But we won't need this, because for us the commutator between fields will always be a number. Okay, now in order to see what kind of problems one encounters, it's actually useful to just look at this product first. Which, according to what I have here, is e to the I alpha phi right of x plus beta phi right of x prime, e to the 1/2 phi right of x commutator phi right of x prime. Okay? So now let me work out, okay, so this is the same as e to the I beta phi right of x prime, e to the I alpha phi right of x. Now what I'm doing is I'm using the Baker-Campbell-Hausdorff in the reverse. Yeah? So I'm rewriting this as a product of vertex operator in the reverse, and then here I will have phi right of x, phi right of x prime. Okay? And the idea now of the calculations I'm doing is these vertex operators will, if I choose alpha and beta in the right way, you can get, for example, anti-commutation relations here. So this vertex operator times this vertex operator could be something like minus this times this. Yeah? If you want to represent these fermions in terms of bosonic fields, you have to make sure that you recover the correct anti-commutation relations. So let me work out what this commutator between phi right of x and phi right of x prime is, and I only do this to show you that there's still some ambiguities present, which you have to cure. Okay, so use the mode expansion. Yeah, just calculate the commutator. So you can do it because you know what is the commutator between the beta n and beta dagger m, and between these p's and q's. Okay, so here you get x prime minus x, and then we have plus sum n equals 1 to infinity 1 over 4 pi n e to the I kn x minus x prime minus e to the I minus I kn x minus x prime. So this is what comes out using the mode expansion. Now the point I'm trying to make is this infinite sum here doesn't exist. Yeah? The reason being, well, it basically goes like 1 over n for large n, and these all have magnitude equal to 1. Yeah? So this is a divergent sum which you have to define. And the way we will do this is by actually just introducing by hand conversion factor. And the conversion factor I simply take e to the minus 2 pi epsilon n. Okay, so now the sum is convergent, as long as epsilon is not 0. Okay, so what I'm doing, in other words, I'm cutting off, or I'm putting a smooth cutoff on the very, very high momentum modes. So I'm suppressing their contributions. And so this is some kind of regulator, smooth cutoff in the theory, and my answers now in the next few lines of calculation will all depend on this epsilon. Okay, so let me see then what I get. So after I've done this, you see you can do the sum now, because the sum has the form n equals 1 to infinity. Let me just call this something, I don't know, whatever, x, x, I can't use x, y to the n divided by n, and that you recognize as the sum of the logarithm. So this is actually log 1 minus y to the minus sign. Okay? And now I will use this to carry out these sums. Okay? And what I find is this becomes I divided by 2L x prime minus x plus 1 over 4 pi ln 1 minus e to the 2 pi over L, the minus sign, x minus x prime, 1 minus e to the 2 pi over L, x minus x prime. Okay, what I've done here is I've taken the sum, and after taking the sum I've taken epsilon goes to 0, which for this particular commutator I can do, and then I get this answer. Right? So you do the usual thing, you introduce a regulator, you take the sum, and then you... Okay. If I wanted to keep it, it actually would be here, minus 2 pi epsilon. Minus 2 pi epsilon. Okay, but then you see I can take it to 0. Okay, now you see this one away. You can take the logarithm, because this is exactly the inverse of this. Yeah? And what this becomes equal is just I over 4 times the sine function of x minus x prime. Okay? So in other words, so this piece will always be cancelled by something that comes from here, and what remains is just a constant. Yeah? Which is this I over 4 sine x minus x prime. Okay. And I was going through this calculation a little bit of detail just to show you what you always have to do. So whenever you work in these modes, you always have to cut them off in this way and carry this epsilon regulator as long as you need to. So, okay, so now, as I said before, what I wanted to calculate was this two-point function, e to the I alpha phi right of x, e to the I beta phi right of x prime, yeah? And using but I just erased over here, I can rewrite this now as e to the I alpha, phi right of x, plus I beta, phi right of x prime, expectation value times e to the minus I pi over 8, it turns out, I over 8 alpha beta sine x minus x prime. So that came from what I had written here. So the product of these vertex operators was this vertex operator times e to the I times the commutator, and the commutator I just calculated for you over there, and if I write it out I get this. Okay? Now this one I can calculate once again using the mode expansion. So now use mode expansion to calculate. Okay, so now I'll do this in two steps. I first will look at the zero modes and then at the finite momentum modes. So the zero modes, I get something which is like this: e to the I alpha plus beta capital Q minus IP divided by 2L alpha x minus beta x prime on 0. Okay, and so this turns out this is 0 unless alpha is equal to minus beta. Okay. So this is delta alpha minus beta. So it's at least proportional to delta alpha minus beta. Okay, the reason is these are canonically conjugate variables. Yeah, so if I look at this, e to the I gamma q, that actually is an eigenstate of p. Okay, you can just do the same once again in quantum mechanics. So this would be e to the I gamma x. Yeah? That would be an eigenstate of the momentum operator. Yeah? But it would be an eigenstate which is orthogonal to the ground state, but with a different eigenvalue. From the vacuum. Yeah, the vacuum is just an eigenstate with eigenvalue 0. And therefore, you would have 0 e to the I gamma q 0 would be 0 unless gamma is equal to 0. Okay, so in other words, these zero modes force these two coefficients, alpha and beta, to be exactly opposite. Otherwise, the correlation function vanishes. Yeah? So this is sometimes known as electroneutrality. Yeah? Now, once I know that alpha has to be equal to minus beta, yeah, so then this term simply vanishes. Then I just have the ground state expectation value of the vacuum of e to the I p times something, but the vacuum is an eigenstate of the momentum operator with eigenvalue 0, so this becomes an identity. All right. So now we have done the zero modes. So now we just have to look at the finite momentum modes. And for the finite momentum modes, you just repeatedly use the following identity: e to the gamma b plus delta b dagger is equal, now using this Baker-Campbell-Hausdorff, this is just e to the gamma b dagger, e to the delta b, e to the minus gamma delta over 2, and here we have b dagger b. So this would be Baker-Campbell-Hausdorff. Yeah, but this is then just equal e to the gamma delta over 2. Okay, because b dagger with b commutator is minus 1, yeah, and b annihilates the vacuum. Alright, so I have this. And now I can do this for every mode. Yeah, for every finite momentum mode. Okay. And then, so this tells me that e to the I alpha phi right of x, e to the I beta phi right of x prime, expectation value, ground state expectation value, is now equal. That's not how so I first look at this, e to the I alpha phi right of x minus phi right of x prime. So I first look at this expectation value, which is this one here. Okay. So that becomes e to the minus alpha squared over 2, sum n equals 1 to infinity, 1 over 4 pi n, and here you have 1 minus e to the I k n x minus x prime, 1 minus e to the I k n minus sign x minus x prime, just using this repeatedly, you get the sum, and this sum now you can treat exactly like we did when we calculated the commutator of phi right of x with phi right of x prime. Because once again, I cut off this sum, I put here e to the minus 2 pi epsilon n, yeah? And then I can rewrite this always as a series representation of this log, minus log 1 minus something. Okay? And what this becomes after the dust settles is just epsilon, which now doesn't cancel, to the alpha squared over 4 pi, for sine squared pi over L x minus x prime, and this whole thing to the minus alpha squared over k prime. Alright? And once again, here the sum you use is just sum n equals 1 to infinity. You have e to the, I don't know, minus gamma n divided by n. So this becomes minus log 1 minus e to the minus gamma n.
No n.
Thank you. So I just use this sum repeatedly. Okay, and so now, first of all, what we have achieved is we have worked out what the two-point function of this vertex operators is. So let me give you the answer. So putting everything together, now you get e to the I alpha phi right of x, e to the I beta phi right of x prime is delta alpha minus beta. And I just skip some other step, I suppose, which would be then I epsilon 2 sine I over L x minus x prime to the alpha squared over 4 pi. Yeah. So the step that I have skipped, you see what you have here, so sine squared, yeah? It's always positive by definition, so I can write this essentially as the absolute value of 2 sine whatever, and then alpha squared divided by 4 pi. So now I have an absolute value in here. But when I was multiplying these two vertex operators, I had e to the I alpha phi right of x, e to the I beta phi right of x prime. That was the same as e to the I alpha phi right of x plus I beta phi right of x prime. And then I had the sine factor, right, whatever it was. So sine x minus x prime. And what happens is essentially that this factor here cooperates with what you get from here, what you get from here, and removes this absolute value, and you end up with this. So it's done in the notes. So I'm just skipping this because otherwise we're not really going to get as far as I would like. Okay, so now we're almost there. If I now take the limit L goes to infinity, or take L very, very large, yeah, then this, while keeping x and x prime fixed, which is what I would do if I go to the volume, then this becomes delta alpha minus beta I epsilon L 2 pi x minus x prime to the alpha squared over 4 pi. Okay? Now, I just need another 5 minutes or so to come to a point where we can take a convenient break. Okay, now what I want to do is, it turns out it's very convenient to work with normal ordered operators rather than the non-normal ordered ones I've used here. Okay? So, what we want to do is we want to normal order. So, we want to work out what is this. E to the I alpha phi right of x. Normal order. Normal order simply means I move all the annihilation operators or expressions involving the annihilation operators, I move those to the right. And the creation operators to the left. Yeah? And you can now simply show that's a reordering of these exponentials you have with the mode expansion. Yeah? And you can work out how this quantity is related to the not normal ordered one. By using once again this Baker-Campbell-Hausdorff lemma. And it gives you once again the type of calculation I've just shown you, and working out the details gives you the two operators are proportional, and the factor of proportionality is the one I'm writing here, 2 pi I x over 2L. So this piece comes from some zero notes. Okay? So the normal ordered expression is the same as the not normal ordered one, but times some divergent constant. So some, when epsilon goes to 0, very, very small constant. Okay? Because once again, in this infinite volume limit I'm interested in, this thing simply will be equal to 1. Yeah? Because x divided by L goes to 0. Yeah? So this one I can drop. Okay, so now we are where we want to be. Combining these two, I conclude that e to the I alpha phi right of x, normal ordered, and then here I put e to the minus I alpha phi right of x prime, normal ordered. So this correlation function is equal, let me put a beta here, delta alpha beta times I. Here is some length scale, let me call this curly L, for example, x minus x prime, alpha squared over 4 pi. Okay? So now this curly L, it involves my regulator epsilon and this system size L. Okay? It's some combination of these two, but all it does, it sets up a length scale in the theory. It's a quantity which tells you how to measure length. Okay? And now there's some ambiguity, and the best way of utilizing this ambiguity, you simply say, let me use this freedom, so to speak, to choose, simply that's a kind of convenient definition, this length scale to be my lattice spacing, A0. Okay? And so this is the standard choice people employ in the literature. It's the most convenient one. And what it is referred to, I mean the words that go with it, you choose the normalization of these operators. These are just words. But there's a regularization procedure involved. And essentially what you do is you arrange the regularization procedure in such a way that your vertex operator multiply in this way. Okay, now the last thing, I know I keep on saying this, but is we can use this result now to make our desired operator identification. Okay? Because you see, if I choose e to the I square root of 4 pi, phi right of x, if I look at this operator, it has the same 2-point function, yeah, as my right moving fermion. Yeah? I had written this for you in the last hour. Yeah, so I had gotten this power law, which was essentially 1 over 2 pi x minus x prime, something like this. Yeah, that was the correlator of R dagger with R. And I can recover this result if I say, well, so let me make an ansatz that my right moving Fermi field is proportional to this vertex operator. Okay, and it's more precisely it's this. And right of x is 1 over 2 pi a0 times this. Okay, so now if you're not happy with the way I treated this regulator and so on and so forth, you see, when you make this identification, you have always a freedom here to put a constant factor, a prefactor. Yeah? This prefactor is completely at your disposal. So if you make another choice here, you simply shift it to another choice here. But when you actually calculate any quantity of physical relevance, these choices don't matter. They always drop out, which is why we stick with this choice. Now, for the left moving Fermi field, you can use something analogous. So the identification that is suggested on the basis of this is the one here. Okay. So this gives me now the correct 2-point function for the left moving Fermi field. There's one remaining complication. These are fermionic, so they should anti-commute with one another. But these two vertex operators, if you just look at the mode expansion, they actually commute. Okay, so we have a problem. Now we fix the problem by introducing what are called Klein factors. Yeah? And these are just some 2x2 matrices in this case. So more generally, so eta bar, so these are Klein factors. So these are objects that simply have to fulfill some anti-commutation relations. The anti-commutation relations that I want is that eta anticommutes with eta bar. Because if I have that, then right and left anticommute. Okay? And then right with right, the eta basically shouldn't play a role, and that gives me that eta squared is eta bar squared equals 1. Now you might say, well, okay, so what are these mysterious objects? Well, the easiest way to realize these, just choose eta is equal to sigma x and eta bar is sigma y. But these are the Pauli matrices. And they actually fulfill these relationships. Okay, so these formulas I've just written for you, those are the visualization formulas. I've motivated for you where they come from. Yeah? Because I showed you that this free compact boson theory had the same spectrum as the free fermion. It's a strong indication that the two theories are the same. Yeah? Now if I want to identify operators, the very least I have to show that the 2-point functions match. Yeah? So these match, so that basically means these are good guesses. Yeah? Now, what you really have to do to close the circle, so to speak, you really have to show that these identifications also work for all other correlation functions, and they do. Yeah, so these, that's the full story. And the final point is, now when I introduce these Klein factors, of course what I did is I introduced unphysical degrees of freedom, if you wish, because now if I calculate correlation functions, they involve products of Pauli matrices. Okay? So, for example, if I look at y dagger of x, L of y, or something involving these, yeah, so this one is actually 0, so it's not such a good example, but just the product would involve a eta bar. Okay? And now if I want to calculate expectation values, I actually have to say, well, expectation value in this Klein space with respect to what? Yeah, because these are unphysical degrees of freedom, I simply put, because I wanted the correct anti-commutation relations. Now, the point is, in any physical quantity that you want to calculate, these Klein factors, and this you can prove, they will only occur in combinations that always commute with one another. That means you can always replace these by an expectation value with respect to a arbitrarily chosen state in this two-dimensional vector space of Pauli matrices. And so, for example, you can say, I always take the expectation value with respect to this state in Klein space. Yeah? And this is like a gauge choice, okay? And that's the procedure that removes for you these unphysical degrees of freedom. And nothing you ever calculate will depend on them. Yeah? Okay, so I've run over a little bit already, so I'll stop here.